Hello again. Welcome back to this course on fundamentals of data science. So we have been discussing about the basics for statistics, and also we discussed some points on probability. And today we are going to extend that topic into a Bayesian statistics. So before we go on to this Bayesian statistics, we will consider what is a conditional probability and the Bayes theorem, which is very basis for the Bayesian statistics. So that is going to be the content for today's lecture. And today we will consider what an event is and what is the conditional probability, Bayes theorem and Bayesian statistics. Eventually these 2 points like Bayes theorem and Bayesian statistics is going to help you in a long run, even in machine learning. Various parts of artificial intelligence as well as machine learning has this basis for Bayesian networks as well. So this is one of the important topics in data science, which can give you a platform to build upon to any of the machine learning methods. So let's dive into the topic right away. Event. An event is something that happens, right? Yeah, that's true with statistics as well. An event can be independent event or dependent events. So in the previous lectures we already discussed about what is an independent event and what is an dependent event. Well, we know that when you toss 2 coins, those coins are kind of independent because none of the previous experiments is going to affect the current one. So event can be independent, meaning each event is not affected by any other events. Just like tossing a coin. Yes, each time you toss a coin is perfectly an isolated event. It is not influenced by the previous toss or the toss to come. But events can also be a dependent, which means they can be affected by previous events. Consider this example here. So you can see there are 5 marbles in this bag and 3 red marbles and 2 blue marbles. So there are 2 by 5 chance of pulling out a blue marble and 3 by 5 chance for a red marble. Just go one step ahead and see. See what happens when we pick the second marble. You can clearly see that in the first step, for example, if you pick up this blue marble already, then your probability might change drastically in the next step, because right now there is only 4 marbles and now your probability of picking up the blue marble changes. So that's what has been illustrated here. So we can consider these events as individual events. Though they are individual events, still each event depends on the previous events. Just like here, you see that if you already picked up a blue marble, and second time when you pick up the blue marble, the probability changes to 1 by 4. Likewise, if you pick up the red marble in the first instance, and for the second instance picking up the red marble, the probability changes to 2 by 4, so on and so forth, because of the previous events. Yes, now you can see that how these events are dependent on one another. With this basis, let's deal more on how this conditional probability works. As the word condition applies and implies, we know that it has to satisfy certain conditions. Just like when we say P of A, which means probability of event A, in this example of our marble, the event A is get a blue marble first with a probability of 2 by 5, the same thing that we have seen here, right? For getting blue marble, it is 2 by 5? Yes, let's consider that as the event A. So P of A is 2 by 5, and event B, get a blue marble second. But for that we have two choices. If we got blue marble first, the chance is 1 by 4, and if you got red marble first, the chance is 2 by 4. You got it? If you got, in the first time if you got blue marble, then your chances becomes 1 by 4 the second time. But in the first instance, if you get a red marble, your chances become 2 by 4 for picking up the blue marble in your second chance. So we have to say which one we want, and we can use the symbol just like a bar, which means given. So you can look closely here. Probability of B given A, that's what it says. P, probability of event B is given, event B given event A, which means that we have event A which is already given to us, and we ought to estimate for event B. So event A has already happened, and now you want to estimate what are the chances for event B. That's what this means. Probability of B given A. So this probability of B given is called the conditional probability of B given A. So in this example, we can see that probability of B given A is 1 by 4. In this case, when we have the blue marble picked up in the first instance. So let's try to build up. So you can see here, step by step you can see what is happening. Probability of A, initial probability, right? Probability of A is nothing but get a blue marble first. In the first chance you are getting the blue marble, and probability of getting the blue marble again in your second chance is 1 by 4. That is probability of B given A. Blue marble first and getting your blue marble the second time. So probability of event B, we want to check that out. So this is the basis for the conditional probability. We know that given a condition, what is the chances for another event. So with this thought, we can define what is this conditional probability is. So probability of A and probability of B, or event A and event B, we can say probability of A times probability of B given A. So just like here, probability of A times probability of B given A. So in this, with this thought, let's move on to some simple examples of drawing two kings from a deck. You have a playing cards and you want to draw two kings. Event A is drawing the king first, the first chance, and event B is drawing a king in your second chance. So for the first card, the chances of a king is 4 out of 52, right? So that's your first option, like probability of A is 4 by 52. Since you know that 4 kings are in your deck of 52 cards. But after removing a king from the deck, the probability of drawing this king, the second in your second chance, is less likely. You can say that only 3 out of 51 cards are there. So that is probability of B given that probability of A has already happened. Probability of B given A. Probability of B given that the event A has happened. So we could write it this way. probability of A and B. So we can say probability of A times probability of B given A. So when you multiply that, you get 1 by 122. So it's about around like very less probability there, around 0.5%. So that's an example. Let's with this example, let's move on and see how things can be worked out. So initially you start with probability of A times probability of B given A, and you can swap this around, and you can also divide this by probability of A. So when you divide by probability of A, you or come up with this form. In other words, we can use this formula. This is quite useful formula there. Probability of B given A equals probability of A and B divided by probability of A. Or in other words, the probability of event B given event A is equal to probability of event A and event B divided by the probability of event A. So here is another real-time example. You can look at this example closely. So you're off to soccer and want to be a goalkeeper, but that depends on who the coach today. With Coach Kim, the probability of being goalkeeper is 0.5, and with Coach Lee, the probability of being goalkeeper is 0.3. Kim is coached more often, and about 6 out of every 10 games. That's probability of 0.6. So what is the probability that you will be a goalkeeper today? Well, let's see the two possibilities. Like we right away know that probability of Kim being the coach is 0.6 and probability of Lee should be 0.4. And if you get Kim, there is 50% or 0.5 probability of being a goalie, right? If Kim is the coach, you have 0.5%, or not 0.5%, it's 0.5 probability of being a goalie. And if it is Lee, then it's going to be 0.3, right? So we can put that in this tree graph. You can see you have a chance of 0.5 being a goalie if Kim is the coach. Then for Lee, if he is the coach, then you have 0.3 probability. So we are putting out all the possible probabilities, and we are trying to figure out what happens if probability of A and B equals probability of A times probability of B given A. So when you take this 0.6 chance for Kim being a coach, which gives 0.5 chance that Kim will let you be a goalkeeper, and we end up with this 0.6 times 0.5, which is 0.3. But you can clearly see how it happens. What if Lee is the coach? The same thing applies here. 0.4 times 0.3, which is 0.12. Yeah. So we have this branches out of this tree, which says yes and no. Yes, you can be a goalkeeper, and no, you can't be a goalkeeper. So when you add up these chances with the probability of Kim and Lee, you get 0.3 plus 0.12, which is 0.42 probability of being a goalkeeper today. In other words, you have 42% chance of being a goalkeeper. So can you see that how one event is affecting another event? You are talking about you being a goalkeeper, but that really depends on other factors. So that's how we are building up. So you can see the overall probability of even not being a goalkeeper. So you can see how this is going to be add up. We know 42% you can't be a goalkeeper, you can be a goalkeeper, which means 58 % chance you or not. So when you add this up, it is like 0.58. That is, you don't get a chance. But anyway, if you add all those stuff, you can get 1, the overall probability. Okay, let's move on to this Bayes theorem. As we have seen what is the conditional probability, and now Bayes theorems are based on this conditional probability, and we can see how this is going to help us to formulate various cases. So here this has been formulated by Thomas Bayes, and he is in fact contributed a lot to this statistics by means of his Bayes law and Bayes rules. Though he didn't publish his original work, this work in fact was published by Richard Price after Bayes' death. Yes, so basically this is how the Bayes theorem goes on. Here is an example given to us, like if the risk of developing health problem is known to increase with age, then Bayes theorem allows the risk to an individual of knowing age to be accessed more accurately than simply assuming the individual is typical of population as a whole. So he is considering other factors that would affect this particular event. So to be precise, we could say Bayes theorem is also very similar to what we have seen, that is the conditional probability. Yes, when we say Bayes theorem, as you can see, it is applied in various Bayesian interference. So Bayesian probability interpretations can be expressed in various things. Even they have something called Bayes networks, Bayesian networks and belief networks. They are also being formulated, and this Bayes statistic is one of the bases for that. So if you want to find probability based on this Bayes theorem, you can see probability of A given B, probability of A given B equals probability of A times probability of B given A divided by probability of B. So with this basis, we will move ahead and discuss more on this. Here is one example. Let us say probability of fire means how often there is a fire, and probability of smoke means how often we see smoke. So probability of fire given smoke, which means that how often there is fire when we see smoke, and probability of smoke given fire means how often we see smoke when there is a fire. So based on that, let us formulate this whole thing with forward probability of fire given smoke, and for backwards probability of smoke given fire. And there are some information given to us while solving this problem, like the dangerous fires are rare, which means like 1% chance of getting a dangerous fire, but smoke is fairly common, like 10%, because many people might do barbecues and things like that. So smoke is quite common. 90% of chances or 90% of dangerous fires make smoke. Whenever there is a dangerous fire, 90% we see smoke. This is the third factor. So with these factors, let us see what is the probability that we have here for fire here. So probability of dangerous fire when there is a smoke is given to us. So probability of fire given a smoke equals probability of fire times probability of smoke given fire, that is the probability of smoke. So we can see here the probability of fire is rare, very rare event, which is 1%, and probability of smoke given there is a fire. So whenever there is a fire, there is 90% chance that you have a smoke. So we are going to have this 90% given to us here. So eventually you can find that it is around 9% chance that we have. So with this thought, we can see how we can apply this conditional probability to Bayes' theorem. So we can expand more on this Bayes' theorem. We can consider, imagine that 100 people are at a party and you want to know, or you want to tally how many people wear white and how many people don't wear white, and if a man or not a man, when you have guest in the party, you want to consider whether he is a man or not. So probability of being a man is probability of man is 40 by 100, which is 0.4, and probability of wearing white is 25 divided by 100, which is 0.25, and probability of man wears white is 5 divided by 40, that is 5 divided by 40, which is 0.125. So probability that a person wearing white is a man is probability of man given he wears white. We have to check that out. Probability of person wearing white is a man. Probability that a person, the guest who is wearing white, is a man. So with this given information, can you discover the probability of a person who is man and wearing white? So with this thought, we can calculate using this formula here. So in this case, we have 0.25, there is 0.2 here. So it's a raw data, we can also calculate directly. If you look at closely, you can also see that how this is being applied 5 by 25. Well, with this thought, let's move on to some common terms. Even without applying this numbers, you can also see how you can use certain characters to understand what is there and what is not there. We talked about man and not man, white and not white. So based on that, you can see, you can fill this similar structure with S, T, U, V, and you can see you can use the same formula here and apply the same principle for the given problem here. So for example, S plus U divided by S plus T plus U plus V for all of probability of B, and probability of A given B is S divided by S plus U, that is probability of A given B. Probability of B times probability of A given B, we have just S. So with this, you can fill in the information like that, as we have just seen here. Okay, there is more information on false positive and false negative. So this is another feature of the Bayes theorem. Not only Bayes theorem, there are a lot of other areas in machine learning. We always want to consider this false positive and false negative informations, because at times it is of prime importance. You can consider this example here. Here Hunter says she is itchy, right? She says she is itchy, and there is a test for allergy for cats, but this test is not always right, which means that they are not 100% accurate. So the people really do have allergy. So when you take a test, when a person really has an allergy, the test says 80% of time it gives you correctly. But for people who do not have allergy, the test says yes, they have allergy 10% of time, which means that is your false positive. Just like you go and test for influenza, and even if you don't have influenza, you have been tested as influenza, something like that. So if 1% of the population have allergy and 100 tests says yes, what are the chances that 100 really has the allergy? So we know that chance of having allergies when test says yes is probability of allergy given that the test says yes, the person has allergy. That can be written as probability of allergy times probability of S given there is an allergy divided by probability of S. So when I say yes, which means that the test says positive, the person has allergy, right? So P of allergy is the probability of allergy, that is 1% in the population, and probability of yes, the test says yes and the person really has an allergy, is 80%. 80% it is accurate, you can say, it gives the results correctly. And probability of yes is the probability of test that says yes to anyone. So we are not sure who they are, like whether they really has an allergy or not. Let's consider some information. We do not know what the general chance of test saying yes is, but we can calculate just by adding up those with and those without the allergy. So we know that 1% in the population has allergy, and when an allergic person tested, 80% of them are given positive results, like yes as a result, 80%, and 99% do not have allergy, but the test says yes to 10% of them, which means even if you don't have allergy, 10% of them has been stated as they have allergy. So probability of yes we can calculate 1% times 80% plus 99 times 10%, which is 10.7. So with this 10.7 of the population will get yes results actually. So now probability of a person being allergic given that the positive results. So 1% in the population, 80 times, when you calculate it, it gives us 7.48%. So with this information we can move ahead and try to understand what is happening, like probability of allergy given yes is about 7%. So this is the same result as we got for false positive and false negative. So you can use the Bayes formula again in this aspect to check the false positive and false negative. So finally we move on to this question. I leave these questions for you. You can try to solve this question by yourself. It is a simple question related to Bayes' theorem. You have to find the chance of rain during the day. Okay, basically the Bayesian statistics is a theory in the field of statistics based on certain Bayesian interpretation of probability, where the probability expresses a degree of belief in an event. Right? In the previous example we saw that the degree of belief is that 1% of the population has the allergy, but we believe that 80% of the test shows accurately positive, but still there is a chance, like we had 10% we get the false positive in this example. So based on certain belief of an event, we proceed to find the actual probability by means of certain interpretations and experiments. So such interpretations can also be interpreted using frequentist interpretation. In other words, how frequently things are going to be happening and how we can interpret and infer things from those conditions or conditional probabilities or events. So as you can see here, the Bayesian statistics, suppose out of the examples given here, we can see 4 championship race F1 between Nicky and James. Nicky won 3 times while James managed only 1. For example, if we have to bet on the winner of the next race, whom you would bet? So that's the question. So let's bet on Nicky. But if there is another condition, what if we are told that it rained once when James won and once when Nicky won? So now things are getting different, right? Whenever there is a rain on the next date, who would be the winner? Now the chances for winning changes drastically for James and Nicky. So based on that, the Nicky's effort and James' chances have been changed drastically as well. That's why. So one event can affect another event, and another thing is like as we have already know some information about rare event, the frequency of the event can also make a huge difference. To understand the frequency statistics, you can also think about tossing a coin. So we know that whenever a coin is tossed, there is 0.5 probability of getting head and 0.5 probability of getting tail. But as you increase the number of times, theoretically they have to remain the same, right? The number of toss you put, the number of heads you get should always be 0.5. That is what we know, the fair thing to happen. But as you can see from this table, when the number of tosses increases, you can see the chances are changing. For example, among 10 there should be 5 initially, but only 4, which means 1 different. And among 100 there should be 50, but there is actually in the actual experiments only 44 came out, so the difference is 6. But as you increased to 10,000, there should be only 5,000, but we got 5,067. Yeah, that is one of the interesting facts, that people found that when we increase the frequency of a certain event, there may be a chance that the whole probability measures might be biased in some ways. So that's what we saw today. We talked about what is an event, how a conditional event or conditional probability can influence the overall events. When one event happens, such as the dependent event, depending on the previous events, we call it as a certain condition has been happened. Given this condition, we are trying to calculate another probability. And Bayes' theorem is also based on this conditional probability. We talked about Bayes' theorem. We also talked about some examples of Bayes' theorem. Finally, we gave some instructions on Bayesian statistics. So that's a brief summary of what we have seen today. And I recommend that if you have if you want more information, you can also look at this website. It's very interesting. Math is Fun, which gives you very clear instructions on most of the probability and statistics in a very fun way. And what is in for our next session is, we are going to discuss about mean, median, mode, standard deviation, variance and covariance. So that's what we have for our next session. I'll catch you there. Until then, goodbye.